Truesdell, more recently of a new initiative at the University of Pennsylvania called Integrated Language Science and Technology. Professor Yang has a forthcoming book from Oxford University Press called Language Acquisition, a slim guide and a simple theory. He is also the author of The Price of Linguistic Productivity, How Children Learn to Break the Rules of Language, published by MIT Press in 2016. And it was also won the Leonard Bloomfield Award from the Linguistic Society of America. In 2017, he was also the co-editor with Norbert Ornstein, Howard Lasnik, and Rudy Mateo Gross of the collected essays volume Syntactic Structures 60 Years On, The Impact of Chomsky's Revolution in Linguistics. Today, Professor Yang is giving a talk on how language makes us smart without big data. Please join me in welcoming Chomsky.
Many thanks. Can you hear me okay? Good, right. So indeed, I miss Sam. He was one of the very first linguists I met, and he was very kind to me when I was just a beginning computer science graduate student. He took me seriously, and he showed me some of his work, very elegant. It was one of the reasons I was attracted to linguistics. It's very unfortunate not to see him here. I think I miss him like many of you do here too. Okay, so let's talk about language, how language makes us smart. This is not a new idea, right? So language shapes the way we see the world, we conceptualize the world. This is something that's been discussed for a very, very long time. So I'll give you a little bit like a simple experiment. So I'll give you the picture of this thing. Okay, I'm going to ask you, is this a blickle or is it a blicker? Who thinks it's a blickle? Who thinks it's a blicker? Who thinks it's a blicker? Can I see a raise of hand? Who thinks it's a blickle? Okay, so why do you think it's a blicker? I mean, so without becoming a real experiment, I think a lot of us would see this as a blicker because whatever this is, it looks like a tool. Okay, it's actually indeed, I think, a 17th century farming tool or something, right? The reason we think it's a blicker because, of course, in this word, there's an ER ending to it, right? Blicker, ER is an ending in English that denotes agency, that denotes instrument, and so on, right? So if you hear something as a blicker, you might instantly be looking for the meaning of blick as a verb that, you know, whatever this tool is used for, right? Where blickle, it's almost like it's a simple word. It does not consist of individual pieces that has associated meanings, right? So this is what I mean by language shaping the way we see things, right? So here's an object that, depending on how you hear the form of a word, you may develop some appreciation of its features, of its properties, right? Now it's very interesting to emphasize that ER is the ending of English. It's something that people here have learned over the years. It's not a universal feature of all languages, right? So what's required is really a process by which we learn ER is a active piece that plays a functional role in the English language that has certain systematicity to its form and its meaning. And notice to learn this is actually not easy, okay? Because not only you hear words like kick, kicker, drink, drinker, when it's very clearly, or very clearly a verb related to its instrumental agency, we also hear words like letter that are not related, or corner, for that matter, right? So whatever we do to learn the feature of ER, which is a feature of English, we have to overcome the noise to detect the signal that is the ER is really serves the function of whatever the form and meaning mapping is in our language. So that's really the driving force behind all of this, is how do we detect such systematic relations between form and meaning in language as children before we start taking grammar lessons. So this idea, again, goes way back, right? So language is really a key that makes us so much more sophisticated than other guys, especially from a perspective of evolution. We know we haven't been separated from them for a very, very long time, so it's probably not conceivable to evolve all our cognitive differences in this very short span of time. And of course, the one non-negotiable difference between us and them is language. So a lot of people have had the idea that the language is really behind all these complexity or differences between us and other animals, including very closely related ones. So today I'm going to focus on one thing, right? So the thing of number capacity, to the ability to appreciate symbolic numbers, right? So only humans have language. This we don't much doubt. And also only humans have the full capacity of what's known as symbolic number system, right? So this is to really appreciate this notion of infinity. You can train an animal, non-human animal, by rote. They can learn up to maybe 20 or maybe even 25, but they never seem to be able to generalize beyond the finite experience they have. But of course, all humans are capable of doing so. Well, nevertheless, it's not, so a lot of people have thought language and number to really the same process, but there's some complications. For instance, we know people probably have been talking for maybe 100,000 years, if not longer. But there's no evidence for anything approaching or resembling mathematics until fairly recently. So these are some of the oldest mathematical artifacts. I think they're from the Republic of Congo. Those are bones that clearly seem to be marking devices. And these were probably appeared about 40,000 years ago. So we probably have been talking for 60,000 years before we developed the number system. And the question is, why do you have this gap? You know, as we'll see, there's still cultures that that still don't have the symbolic system as we understand it, which raises interesting questions. Okay, so here I'm going to play a little bit of video for you. This is from this is a little boy named Reed. He's the son of my colleague in computer science, Chris Kelton Birch. I believe he was a MITRE speaker here a couple of years ago, but he's an NLP researcher. So this is a Reed learning to count. Okay, so if you have children, you know children eventually learn to count. They make a lot of interesting mistakes, as Reed is going to do here. I hope you can hear the audio. Oops.
Hey, I'm Rosen. 14, 15, 16, 17, 18, 19, 20, 21,
22,
23, 24, 25, 26, 27, 28, 29, 30, 31, 12, 12, 13, 14, 15, 18, 2019, 2017, 2012.
What it does is actually reasonable, right? So imagine you're learning English. You have 1 to 10, completely unrelated random words. Then you have 11. That doesn't seem to bear any relation to 10 and 10. 1, 12. So why not 12 teen? So what the child is doing is actually perfectly sensible, right? So if you have children, you know that sometimes they can recite a sequence of numbers without understanding anything about what those numbers mean. I hope you have this experience. And it's almost as if they're reciting the alphabet without knowing. I mean, of course, the alphabet itself does not really mean anything. It's purely a sequence. But imagine you're reciting. You can count from 10, 1, 2, 3, 4, 5, 6, 7. They have nothing in common whatsoever. You're really memorizing a sequence. But this sequence has to stop at some point, right? So everybody learns to count at some point. And you learn to count. You know the counting the sequence can go on without having to count literally an infinitely long sequence, right? So there's got to be a point where you figure out what the pattern of counting. I hope this is clear, right? So because you learn an infinite sequence of counting without having to count so infinitely, there's got to be a tipping point where you figure out, I've got the rule. That has to be the case. There has to be a tipping point somewhere. So to my great surprise, I was at a workshop 4 years ago, and where a lot of things came together. I was greatly surprised that there's a tipping point that seemed to be 72. So here's a work by Karen Fusong. Is it a pointer? All right. Here's a work by Karen Fusong. So they were looking at, and some colleagues from the 1980s, they were looking at a bunch of American English learning children counting. They want them to count as high as possible until they couldn't go any further or until they were making mistakes. So you can see some of these are typical. Some kids couldn't count past 10. Some kids couldn't count past 14 or 15. 15 is very hard. That's a classic Sesame Street cartoon teaching kids to count to 15, because kids would count to 14 and skip 15, go to 16. The reason is kind of clear, right? Because once you hit 14, you almost got a pattern. You can put 4 and teen. Then you get hit in the face with 15, which is now 5 teen. So it's actually natural to have a trouble with. So a lot of kids stop over there. Then 20, of course, 20 has to be memorized because 20 does not bear any clear relation to 2 and 10, then 30, and then she says a mysterious number there of 72. This table is given as these are some of the key transition points in children's counting errors. So when I saw this number, I was very excited. So I wrote to her and said, why 72? And here's Karen, who retired in California. She said, because children take off after 72. So there seems to be roughly the tipping point when you figure out the counting system of English. So in fact, there's a lot of studies where you let kids count as high as possible. It's very hard to find kids who would stop at, say, 80 without going all the way to 100. Most studies, you let them count to 100, then you stop, right? It's actually very hard to find children who stop at, say, 85 without going all the way. So it seems like low 70 does seem to be a tipping point where we go there, you got everything figured out. Now, if you know any other language, you know this may not be universal. It turned out it's not universal, right? So kids learning Chinese get this much earlier. Again, if your parents are familiar with children learning these languages, you can see. So this is a work actually by Kevin Miller, who I believe is now here at Michigan, but this is done when he was earlier, elsewhere. So this is comparing the counting range of American kids and Chinese kids. So if you see it for 3-year-olds, there's no differentiation. They basically would stop in the teens. But at age of 4, there's already a big difference in the median counting range between Chinese kids and English learning kids. But at age of 5, almost every Chinese learning child could count to 100. And whereas you can see the median counting range is still in the 60s, 50s and 60s for American English learning kids, right? So everybody understood. This is because the Chinese counting system is much simpler, so it's easier to learn, right? So the question is, how much easier to learn? And then, so what about French? Or what about Hindi? I heard Hindi has a terrible unit counting system. Bernard Comrie even said that well-known typologists argue that every number between 1 and 100 is irregular and has to be memorized. Okay. So the counting process appears to take a long time, maybe by the age of 5 or possibly older. But understanding what those numbers mean appears to be even harder. It's not so hard for small numbers. Right? These are pretty well-known results. If we know infants at a very young age know kind of 1 plus 1 is 2, not 3, or 1. And this is a study with monkeys. Apparently, under suitable paradigm, monkeys also appears to know 1 plus 1 equals 2, 2 plus 1 equals 3. They can't do much beyond that, but they appear to know innately. But as you can see, when you go to slightly larger numbers, you can see very young infants can distinguish the quantity of 1, 2, 2, and 3. But between 3 and 4, they're no longer capable. They're back to chance. So maybe for very, very small numbers, maybe everybody, other animals, know the precise quantity innately, maybe. But you can't go much more beyond that. The rest would have to be learned. So small numbers are easy, large numbers are hard. They're very hard, turn out. So again, I say, if you have children who can count to some number, they have no idea what those numbers mean. In fact, this has been systematically studied. So these are pretty well-known landmarks in number development. Initially, they are non-knowers. Maybe a kid can count to 10, but without any idea of what this 1 or 2 means. So if you ask them, could you give me a cookie? They give you a pile. So they're really non-knowers. They don't know anything about what those numbers mean, even though they can decide the sequence. Then they become 1-knowers. They can give you 1 object when asked for reliably, but not 2. If you ask for 2, they give you a pile, or indeterminate number of objects. They become 2-knowers, 3-knowers, maybe 4-knowers, and then eventually they become what's known as the CP knowers, cardinality principle knowers. So they know if you do the count, the last number you count is going to be the cardinality of the set. So this happens roughly between, maybe 4 and 5. And turn out Reed, the little boy we saw earlier, was a 3-knower, even though he could count to at least to the 20s. Okay, so he had no idea. He could reliably give you 3 objects. You asked for 4 objects, he couldn't give you 4 objects reliably, as if he just doesn't know what those numbers mean, except for very, very small numbers. But for language, we know kids are very good, right? So these, you're talking about 5-year-olds without knowing what those numbers mean. But for language, for the formal aspects of language, children are very good. Well, this is sort of what I do for a living. I'll give you one example because I think it highlights this idea of small data being beneficial in a way. Okay, so here's the simplest rule possible, right? So in the English language, right? So you have English, a singular noun can be combined with the determiner the and a dog, the dog, a chair, the chair. Okay, so to say the child has learned this rule, we have to say that the two determiners are interchangeably usable with with a noun. If you hear used with one adjective, one determiner should also be automatically transferred to the other one. And this is the notion of merge, right? You can put two elements and put them together to create infinitely many objects that are being argued to be maybe the hallmark or a hallmark of the human language. So here is interchangeable as well. But if you look at the data of what children say and what children hear, you see that actually only a small fraction of the nouns are used with both determiners. This is just a statistical fact about languages, right? So if you look at, so in this case, even though these 5 nouns can both be combined with the and if you look at a corpus of a child speech or look at a corpus of adult speech for that matter, you see the percentage of the nouns that appear with both is actually very low, between 20 or 30%, or 40%, maybe. So for instance, the Brown corpus, written by professional writers, about 25% of the nouns appear with both determiners out of all the nouns that appear with either determiner. Okay, so the percentage of diversity, if you will, syntactic diversity, combinatorial diversity is actually not very high. So some researchers have argued that this is evidence that children don't know the grammar because they're really memorizing which particular noun combines with which particular determiner, and that's it. So it's basically a memory-based or usage-based theory of language learning. I think that conclusion is a little too hasty. I won't give you the details here, but what's needed is you need to create a baseline to see that even though it's 20 or 40%, is that low enough to reject the grammar-based view? So I won't give you the mathematical details here, but here I created a baseline, namely you have to take the marginal probabilities of determiners and the marginal probabilities of nouns into account. Then you can, if they're truly independent, you can take the product, you can actually estimate the expected value of such diversity measures in some corpus, and then you can compare that against what children actually produce, right? So for instance, I won't give you the details here, but you can see that's actually right on the line. So even though the ratios of diversity is fairly low in lots of cases, they're at just about as low as you would expect if the combination were truly productive, in the sense that the two categories are truly interchangeable. Okay? So I'll take this as a given, but let's pause and think about why this may be the case. Okay? How do you learn this? What it learns is actually very interesting. So as I say, the grammar children know is the one that each noun can be used with both determiners. But the language a child hears is the one that only has a small fraction of the nouns used with both determiners. Right? As I said, so 20 to 30%. As I said, for instance, this is a typical parent. If you look at the corpus, the mother uses 900 some nouns. Only a third of them are used with both determiners. But what the child's data shows that the child somehow learned that every noun can be used with both determiners. You really have to generalize from a third of the data to all the data. If you think about this, it's kind of bizarre, right? So I apologize for this analogy. Let's take a baseball analogy, right? So if you go out, you're a scout, you go to a scout or baseball team, you see a third of the players, hitters or switch hitters. Are you going to say everybody on the team is a switch hitter? It'd be crazy. You get fired, no? Right? So by switch hitter, I mean, one side is the other side is A, right? So somehow children make this generalization in a completely nonsensical way. So we have to see how this generalization process works. I want to say we don't have to take any position on the innateness issue about language. This rule is a language particular. It's not a universal rule. It has to be learned from the distribution data of English language. So this also goes back to some of the, almost like another lifetime ago when I was still doing NLP, right? So this is a parser. This is kind of, you have a annotated tree bank. You train a statistical parser to to hopefully cover more sentences. And I was struck by, this is the amount of data you feed into the parser. This is the standard Mike Collins parser implemented by Dan Bickel. What you can see is very interestingly that the performance of this parser really shoots up from nothing to about 80%, almost on no data. And then it gradually improves over time. Okay, so of course, if you know the literature, you know the refinement are due to so-called lexicalized rules, namely, basically you see the examples of say, verb phrases headed by particular verbs, then you know what to generalize about the verbs. But otherwise, you're going to default back to the categorical rules that does not make lexical restrictions. So what it's telling us is that because you have such small amount of data, you cannot possibly learn the lexicalization patterns. So the only thing you can learn would be the categorical rules. So in other words, you can learn a lot about your language with very, very little data. And that's really what this chart was telling me. But at the time, of course, I didn't know how to learn this, how to get generalization out of very small amount of data, but I think now I do. Okay? And this is also interesting, right? This is probably now extremely well known. This is the famous 30 million word gap study, where it shows that in American families, depending on the socioeconomic status, children get a lot of differential amount of input, and which translates into very different vocabulary developments over time, which also correlates with lots of other things later in life, right? I mean, there's an important social and educational implication to this, but that's not the purpose today. The purpose today is that if you see a 3-year-old has maybe, if they're very fortunate, they know about over 1,000 words. If you're not very fortunate in terms of linguistic input, 500 also. So you're talking about a 3-year-old knowing something on the order of 800 to 1,000 words. So now if you look at the linguistic capacity of a 3-year-old, it's mind-boggling. 3-year-olds can really put together very complicated sentences, right? So this means that you can learn a lot about your language from 1,000 words, probably the 1,000 most frequent words, because that's where the data is, where the linguistic input data is coming from for the 3-year-old, right? So now if you could push it even further back, for 2-year-olds, right? So 2-year-olds, I mean, they may not talk a lot, but you can do behavioral studies to know to probe their grammar. They know a lot about the grammar. So they are learning this on maybe 200 words. So if you divide up into part of speech, maybe 50 nouns, maybe 50 verbs, I don't know, right? So so we're really learning a lot about language in a very, very small amount of data. So we know humans are capable of learning a lot about language on very small data. Again, we estimate maybe children hear about 5 million words a year. So 10 million words, which is really nothing in this day and age, they can get a lot out of their get a lot of linguistic irregularities out of data. That's something we would like to go after. Maybe after figuring that out, we can start building useful NLP tools. So here's my day job, right? So I've been obsessed with the problem for a long time. This is also a probably extremely well-known problem in cognitive science. There used to be something called the past tense debate back in the day. Here's the the poster child of English past tense debate, but a child by the name Adam, who has a lot of data in the public domain, so you can track Adam's past tense development. And this is the famous U-shaped curve, right? So to make a long story short, you can see Adam initially was not making any mistakes on irregular verbs. Every time he used an irregular verb, he used it correctly. But then right before the age of 3, he started to over-regularize. Namely, he started to make mistakes by using ed form on the irregular verb. So he actually said on that day, what that feel like. Feels not from an input. It has to be the spontaneous error of the child. So that means it's generally taken as mean the child has to learn that ed is a general rule that's going to apply to verbs that he was actually, in fact, producing correctly early on. So here's a tipping point, that the child was not generalizing, but now it's all of a sudden generalizing. And these are equally interesting, although it's not usually talked about together. So these are the marking of regular verbs, by which I mean the following, right? So this means that for the regular verbs, initially Adam was not marking them consistently. So this means that, say, if you take a verb like walked, right? So this means that before the age of 3, 20% of the time when Adam should have used walked, Adam actually said walked. The other 80% of the time, Adam left the verb bare, saying things like, I walked home yesterday, without the ed. But as soon as the child learned ed as a general rule, right, you see this, the consistency of past tense marking really shot up, almost overnight. So this means that Adam really learned that ed marking is the general form in my language. It has to be applied, consistently. Before this, he was really having this item-based knowledge of particular verbs without being able to form a generalization. And this doesn't happen overnight. Lots of things in language are learned very early. This is one of the cases where the children don't learn this overnight. The problem is turned out to be much harder than English past tense. It's easy to come up with a story for English past tense, which is why this project took a long time. I want to give you a taste of the diversity of languages out there, so to see the problem of learning what's a productive rule, what's a generalizable form is not trivial. And here's a well-known problem, right? So in German, there are 5 endings for nouns to form a plural. What's interesting is that there's a minority form of adding s, which is certainly not a majority, but it's actually productive. You can find things like iPhone, iPhones, which is always the hallmark for form being productive. When new words come into language, does the ending automatically sync to it, right? So this is one of the cases. The other case is also puzzling, right? So has to do with English, the stress of English words. So here's a pair. They permit you to get a permit, and they will record a record, right? So depending on the noun or verb, it's stressed differently. And Old English was a Germanic language, basically initial stress. And then due to language change, really due to contact with Latin and French, the grammar changed so that now, for these pairs, nouns and verbs tend to be stressed differently, okay? But if you look at the statistics overall, you see that still vast majority of the words in language are stressed first syllable. But evidently you don't generalize, right? If you were to generalize, you would be assigning initial stress to all the words as a default. It's not even 84% of a majority does not guarantee you can generalize as a default, and you have to do much more complicated analysis of English stress words, as the phonologists here will no doubt know. So the question becomes, how do we learn rules, right? So this work took me a long time. Although I solved this when I was a relatively young man, I did this in my 20s. But the solution turned out to be kind of crazy, so I didn't really pursue it fully until in recent years. If you think about this problem, it's no different from other domains of learning or generalization. So let's say you go out there, you try to catch some Pokemon, right? So let's say it took me a long time to get all these pictures. So if you go to an island, you find that 18 Pokemons are fire monsters, okay? Then it's very easy for you to generalize. The next one is also going to be a fire type, no doubt, right? You would even do so if 2 of them are exceptions. 16 out of 18, I can generalize. No problem. I hope you agree, right? But what about you do things a little bit differently? So what if you go to a place you have 18 examples, 9 are one type, 9 are the other type? Would you be willing to make a bet? Maybe not. Maybe not so sure, right? So what I'm appealing to you is really a common sense notion, that is that if a set of items, if most of them generalize, have property, you're likely to extend the property to the rest. If a very small fraction of them have a property, you'd be crazy to do so, right? So what is interesting is exactly what the threshold is that would warrant generalization from data. So a pattern that can be extended, projected from a subset of data to all the data. That's where generalization in language comes in. So to think about English past tense then, you learn a bunch of verbs. Some of them add ed, some don't add ed. Do you generalize or not? So what Adam did was evidently at some point he learned enough regular verbs. He decided that that's enough. I'm going to generalize. That's you find this pattern. Otherwise, Adam is going to say, I'm not going to generalize. Even though I learn 100 words and 30 of them add ed, I'll be crazy to generalize the 30 to 100. Just like the case of the determiner case I had earlier. So the question is maybe a much more general one than language. That is that If a set of items, many of them do X, you want to say everybody does X. You probably have to memorize the exceptions. But if very few of them do X, you just don't generalize at all. You just memorize those that do X, and that's that. Okay. So here's a little formulation I had wrote up in a book a few years ago. And for the computer scientists here, I want to give you the intuition of where this result comes from, right? So we're thinking about take something like rules plus exceptions, like past tense exceptions, irregular verbs that don't add ed, and regular verbs that do add ed, right? So you can think of this, as a computer scientist, you think about how do you implement this? I really don't know any other way of doing this other than have a bunch of if-then statements, okay? So this is, you list exceptions, and also you add a rule. This is how you would write a computer program to the English past tense. The alternative is to say that there's no regularity, I'm going to list everything by their frequency. So what I'm suggesting here is that it's really a calculus, the cost-benefit calculus the child is doing to find the more efficient way of organizing this list of words, in the sense that you want to maximize the time complexity of these two data structures. You're going to pick the one that's cheaper. I mean, so in other words, in this case, you're going to sort everything by their frequency. This one would take one step. This one would take 2 steps, and so on. And so you get some weighted average. And over here, the irregulars, exceptions, has to be sorted and traversed all the way through. But for all the regulars, you have to wait. You can only access a regular form if all the irregulars have been scanned through and rejected. So this would set up a calculation that would enable us to solve the value for E, namely the maximum number of exceptions that would make this data structure less efficient than listing everything. So this is the intuition behind this, right? And turn out there's a very neat closed form solution to it, right? So this is what I mean by the tolerance principle. So in other words, if you have let's say the child learns n words, number of words in the vocabulary, a subset of them follow a rule. Okay, so the child is going to generalize if the number of items that follow a rule is at least n minus the threshold, where the threshold is defined as n over the natural log of n. You think about it in terms of past tense would be like, of 100 verbs, 70 of them take ed, 30 don't take ed. Is 30, how does 30 compare to n over the natural log of n? For 100, this happens to be 22. So in other words, if you learn 100 words, 70 add ed, 30 don't add ed, you don't generalize. But if you learn 100 words, 85 of them add ed, the other 15 don't, then you do generalize. So here's some non-values, right? So if you learn 10 words, you can generalize with 4 exceptions. If you learn 100 words, you can generalize with 22 exceptions, but no more than that. So you can see the tolerated number of exceptions goes down sharply as a function of n. So this means that it's actually easier for you to detect the signal when you have a much smaller vocabulary size. That's probably the case for the young child early on, right? Children don't, to say, at the age of 2, children know 200 words or so, and that's partitioned into different parts of speech. So I want to give you, this is quite a range of evidence for this. I'll give you some behavioral study, then some quantitative results, right? So here's, you all know this is a WOG test, right? You can buy a t-shirt or mug, but make sure you pay royalty to Jean Burko. She's not so happy seeing all this merchandise over the internet. So here's the WOG and WOGs, and this is interesting. This is a man who knows how to glean. He's gleaning. He did the same thing yesterday. What did he do yesterday? Yesterday, a lot of adults would volunteer glan or galang, but children almost always say gleaned. They don't play language games, with you. Children's understanding of the rules is sharply categorical. They either generalize or they don't. But here's an artificial language study I did with Katie Schuler, Nai Pei, and Alyssa Newport at Georgetown. So we designed, they designed artificial language that has a plural marker. And this language was designed to test the so-called tolerance principle. So here you got 9 nouns. You can see those are so-called toaster language, because everything is like a toaster. So children are introduced to these nouns. In the one condition, 5 of them take share ending. So this is a rule. This is regulars. Then the 4 of them are irregulars. In another condition, 3 of them are regulars and 6 of them are irregulars. So why do we have the split? Because if you put n equals 9 there, you do the threshold is 4.2. So in other words, you predict children in this condition to generalize the pattern categorically, and children in this condition not generalize the pattern at all. So I was, and they, once they did an experiment, they called me, well, your thing worked. So I wanted to see with my own eyes. So I brought my daughter down to the lab. She was the right age at the time, so I'll show you a little bit of video clip of how the experiment worked. Right? So children would hear, and I repeat after the computer, gentive mog ka. Gentive means this is, or these are. Mog is the new word of the green toaster. Ka is the plural, and you can see ka here is the singular. Sorry, mog is the singular, so it's no ka. And here's a plural, so it has ka. Some other items, like po, timbre takes po, which is not one of the regulars, right? And this is how it goes. The child just listen to this and repeat after the computer. It goes like this. This is my daughter at the time. It was a few years ago now, 5 years ago now. She was 5 at the time. Here it is. Oops. Should be able to see it.
Gentive, Clydum, bad. Gentive, timbre. Gentive, spad, ka. Gentive, timbre. Gentive, mog, ka.
So she was in 5-4 condition, so 4 or 5 of them are regulars and 4 are irregulars. And afterwards, afterwards they're giving a real walk test. They were giving nouns they've never heard before. They wanted to see how they express the plural marking. So this is nog. A nog is not one of the words in a stimuli. And they want to see if the children say gentive nog ka or gentive nog something else.
Gentive, flugit. Gentive, blagen. Gentive, geed.
There are no exceptions. So every single token should produce ka. For every, I think there are 20 nouns, should produce ka every single time. So here's a 5-4 condition. This is essentially categorical. Turns out that this is other because for one child, one annotator heard ka, the other annotator heard car. So they had a disagreement of what that is. So this one is the other. If you discount this, then everybody is use ka for 20 out of 20 items, so for every single child. On the other hand, in the strict 6 condition, it's very interesting. You can see the most common response is to sit there and say nothing. They don't add anything because they just have no idea what the pattern ought to be because none of the forms clear the threshold of productivity. And what's interesting here is that you see the solid lines, right? So those are the token frequencies of ka in both conditions. So a lot of her previous work, Newport's lab found that children would generalize the most frequent form. That's not what's happening here. If they were generalized the most frequent form, they'll be producing ka in both conditions. This is not what's happening here. I can have more to say about this in case you're interested, including some more challenging conditions for children. In every case, the principle has been confirmed. Yeah?
How did you come up with that condition of anti-log?
That'll take a little bit longer to explain. But one thing I will say about this where the log n comes in, right? The log n comes, one of the assumptions I make is that word frequencies follow Zipf's law. Okay, so if you follow Zipf's law and you work out the probabilities of words, which is important for weighing the time complexity of the access time, you end up with a term called the harmonic number, 1 plus 1 over half, 1 over a third, to 1 over n, where n the total number of words in the vocabulary, right? So that, to use a result from calculus, that number is approximately the natural log of n. So that's where the term comes in, right? So maybe but many more than that, I probably have to wait for some other time.
You have to use some kind of parameter to take into account that the amount of effort it takes to learn an exception.
Surprisingly, no. This model is parameter-free. Well, as Alyssa would say, this is a theory that's begging to be disconfirmed, right? So let's try it, right? So it's parameter-free. In fact, I mean, there's many reasons why this shouldn't work, but it does. So let's just go with it, okay? Let's just go with it for the moment. I can be happy to talk your ears off at some other point. So now you can understand why it takes so long for children to learn the English passage, at least for this particular child. For Adam, you can do a little bit. You can do some reasonable work. So in this study, because Adam has a large corpus in the public domain, you can extract every verb that Adam produced up to that point. So he produced about actually exactly 300 verbs, out of which 54 are irregulars. It's very close to the threshold that we're predicting, right? So this means that in order to learn a rule, you need a supermajority of the positive supporting items in order to generalize. 50% maybe the intuition, like if something works more than half the time, we should generalize. No, nowhere near, right? So unless you're dealing with a very, very small n. So this is again, consistent with what we know about vocabulary size estimates from children of that age group. Now we can see why this. We can resolve this paradox of how children learn something with a very small amount of data, right? So as I said before, they learn the two determinants are interchangeable, even though only a third of the data supports it. And here's everybody's favorite picture of developmental studies, right? I'm sure I've seen this before. And it actually contains a kernel of truth. So if you look at the distribution of any linguistic rule, it's going to follow this law. There's no doubt about it, with a long tail of sparsity. So effective strategy is to actually ignore the tail. And in fact, children are in a position to ignore the tail because if you're age of 2, you only know 200 words max. You only know maybe 80 nouns. Chances are those 80 nouns are the most frequent ones in your linguistic environment. So even though you're hearing 900 nouns, you're not learning from even a small fraction of them. In fact, this is easily confirmed, right? So if you, again, with all the nouns, only 40% of them appear with both. But if you only keep to the top 50, the vast majority of them would be appearing with both determiners. If you talk to a top 187 of them would appear with both. I mean, that easily clears the threshold that the equation requires, right? So it really sees that if you generalize n to a very large number, to 1,000, the chances of you hitting the threshold is virtually 0, because sparsity is going to kill you. So this is one of the concrete cases. I think it really pays to start small. The children's cognitive limitation may be turned into its advantage if the learning system follows the kind of thresholding property I was describing that favors smaller n's as a sample size, as a vocabulary for which a rule is relevant. All right, so now we can move on to the number stuff. That's fairly recent work, right? So the idea here is really, it's an old idea. That is a language. What's a language? Language provides a systematic mapping between form and meaning. The key term here is systematic. Okay, basically we're talking about learning linguistic rules, how rules can systematically encode certain linguistic relations and enable children and adults to generalize. Children are very good rule learners, and also we know that rules are easier to learn with a small n. The systematicity, of course, is what gives us something, gives us everything from something, right? Because our perceptual or direct experience is always going to be limited. You may know innately 1 + 1 = 2. Your parents may help you count to enumerated marbles. You may know 5 + 1 = 6, 7 + 1 = 9. Sorry, 7 + 1 = 8. But nobody's going to count 25 marbles with you, which is 26. But even if you were to count to 25 + 1 = 26, it still doesn't guarantee this is going to be true for all numbers. So you have to generalize from finite experience to infinity. This is a point that's recognized by everybody. And I hope the theory here is going to give you something new in this direction. So here's what's driving a lot of work in conceptual development of number, and as well as in the foundation of mathematics. This is something so-called the successor function. Right? Successor function, of course, tells you the next number, every number has integer has a successor, which is exactly 1 greater. So Sue Kerry had an interesting theory of how children learn successor function. Right? She believes that when children become the full knower, they become a cardinality principle knower, CP knower, they become successor function knowers. Okay, so if you recall from earlier, children go through stages from 1 knower, 2 knower, 4 knower, then become CP knower. So here's a task where the task is this. So I'm going to give you 5 marbles. How many marbles are there? Children say 5. You have to make sure because sometimes they don't pay attention, right? You say, here are 5 marbles. I'm going to add 1 more marble to it. How many are there? Are there 6 or 7? You have a binary choice. And every child is tested can count to up to 10 at least, right? So what you can see here is that for this so-called unit task or successor task, children who are not quite full knowers yet are below chance or at chance. When children become CP knowers, they are much better than chance. But they're not great, okay? 67% is not great. And in fact, in this study, a well-known study, but only tested on small numbers up to 8. But of course, knowing 7 plus 1 equals 8 does not mean you know successor function for all the numbers, right? At the very minimum, you have to test a larger range of numbers. So indeed, if you test on larger number of numbers, kids don't get it. Okay, so here's a study where, in this study where every child could count to say 50. And then you give them a task. There are 36 marbles or oranges in this basket. I add another one. Are there 36 or 37? The response is chance. It's very surprising, even though they can enumerate the sequence from 1 to 50 or 60 without any difficulty at all. They do not seem to know the relation between numbers, successor numbers, even though they know one comes after the other. It's almost like they're remembering the sequence of alphabet without knowing what those numbers, the semantic content of what those symbols stand for. So now we can finally answer why 72, right? So this is work I started about 4 years ago. So with that workshop, not knowing what to say about language and number, I realized I can say this. So let's think about counting as learning as like past tense. Okay, many of the counting numerals, number words in English, follow the rule of counting, but some don't. So in order to generalize, the number of regular numbers or number of regular numerals would have to outweigh the rote memorized irregular numerals. So let's count up the number of irregular numerals. They're highlighted in red. So 1 to 10, obviously, 11, 12, 13. 14 is okay, 15 is a problem. It's not 15. Of course, all the other teens are fine. 20 is not tutti, 30, and 50. So you count up the red numbers. There's 17 of them. So the 17 numbers you have to memorize by rote. Okay, 17 irregulars. So what is the smallest n such that n over the natural log of n is 17? Okay, so I hope you get this. So if you're able to count to n such that n divided by the natural log of n is 17, you're guaranteed to have overcome the irregular rote memorized words to induce the productive rule for counting for the English language. That number is actually 73. So the smallest n possible to give you this generalization for counting. This is consistent with everything we know about English children's learning of counting on the one hand, but also their understanding of number knowledge, right? So as I said, very hard to find children who would stop at 80 without going all the way to 100, even though the task of counting is kind of challenging. At the same time, here's a more recent paper showing that if you look at children's counting range, it seems like only what they call the very high counters, namely kids who could count to 80 and above, suddenly show the systematic knowledge of successor function. Namely, for any number you give them, they can almost always give you the right answer. Namely, there are 69 oranges in this basket, and another one, are there 70 or 71? They will consistently give you the right answer. Prior to that point, they are very iffy. All right, so now let's look at the other language I know something about, which is Chinese. So here's the Chinese counting system. Okay, you don't need to know Chinese to know this is highly regular. So I'm highlighting things in red. So 1 to 10 are idiosyncratic, you have to memorize, right? Then 11 is really 10-1. And then all the other teens are 10-2, 10-3, 10-4, and so on. Well, this you have to memorize because the order which the decade word and the digit, which one, sorry, the teen and digit, which comes, first you have to you memorize. That's a linear, sequencing. At the same time, 20 has to be memorized because the digit goes before the decade, right? So you have 12 numbers here. So what's the smallest n that would tolerate 12 exceptions? Well, the answer turned out to be 46. Okay, so that means that if you were able to count to 46, if you're learning Chinese or Japanese or similar languages, you should be able to learn the rules of counting. That's, again, consistent with what we know before, that is that they're really learning a much easier language, right? So maybe that's old news, but the real interesting thing is that what does counting, having productive counting system mean when it comes to a child's conceptual semantic understanding of numbers? This is where it gets interesting. So you're really, if I'm right, that is that learning the meanings of those forms that need to generalize beyond any finite experience is really driven by learning the productive form of their encoding. Then you make a quantal prediction. You predict that if it, let's say these are Chinese kids, right? So Chinese learning kids. If you say that if you're not, can't pass the threshold, they should have no understanding of the successor function. They may have item-based understanding of some very small numbers where their parents help them enumerate, but that doesn't go beyond, 15 or something, right? You're really impossible to exactly learn numbers by rote when it goes to a modest size. But you also predict that as soon as they can't pass this threshold, they should go all the way. If you have a complete understanding of the successor function, it's really an either-or kind of thing, making a kind of radical claim of what's happening. So let's put this to test. Right? This is work done with, it's really done in Hong Kong. It's Cantonese, so I don't know Cantonese at all, so this is really done by my colleagues Margaret Lei and Thomas Lee at the Chinese University of Hong Kong. But the Cantonese has the same counting system as Chinese, so it's really, so everything carries over. So it has 124 Cantonese learning children at an age range of between 3 and 6, mean range of about 5. Interestingly, there's no CP knower difference. There's no CP knowledge difference between kids in Hong Kong and kids in the US. There's a very recent paper in Chicago by Spappen and all showing that the mean age of American English learning children become CP knowers about 4.8 in age. You can see the kids in Hong Kong is about 4.9. It's about 4.7. There's no meaningful difference in when they reach the CP knower stage. But we'll see for successor functions, there's a big difference. That's really facilitated by their simpler language. So the first step is to do a counting range assessment. We're going to count as high as possible until they make the first mistake. And this is a standard task. We find that the mean is 61, median is 59, almost identical to the earlier study by Miller. Not surprisingly correlate how high you can count correlates with age, but not with gender. Okay, the older the kid is, the more likely they're going to learn sequence because they hear this counting experience more regularly. All right, so here's a task, right? As I said, you can't just use small numbers because you can always learn a small number by rote. So we divided into this. You can see there's some medium numbers and some high numbers. The medium numbers are low enough so they'll be available for testing for children who couldn't count past 50. Remember, 46 is roughly the cutoff line, right? But they're also large enough so you can't plausibly learn them by rote. You're never going to learn the exact quantity of 23 by counting marbles from 22 into 23. But for those numbers above the threshold, so children are only tested for the numbers within their counting range. You don't want to test kids on a number they couldn't count to. Then the task becomes a linguistic one. So here's the task, the standard task as in this business of testing successor function. I don't know, this is probably 23, I don't know, or maybe 31. hey, there are 31 oranges out there. How many oranges are there? You have to ask them again, just make sure they pay attention. 31. And another one, are there 32 or 33, or 33, 32. They're giving a binary choice, then you move on to the next number. Every number tested is within the child's counting range. Okay, so that's it. And so, of course, not very surprisingly, almost everybody knows 5 plus 1 equals 6. So small numbers really doesn't tell you anything deep about the successor function. So there's a couple of things we can do here. So one thing is that how good is our boundary between 46 plus, just around 46, right? Because we predicted a quantum change between, if you couldn't count past 46, you don't know anything. But if you could count past 46, you should know everything. Okay? So you can do this in a quantitative analysis. There are various ways of doing this. You can say that let's classify someone as a successor function knower if they're tested on at least 5 numbers, they got 80% of them right. If they couldn't get 80% right, then they don't know anything. Okay? You can do this as a empirical classification of knowers and non-knowers. Then you want to see how good your counting range is as a classification. So ideally, it should line up perfectly, right? So ideally, so if this is the kids who could count past 46, this were the kids who couldn't count past 6, you ideally want this area to be all green and this area to be all pink, because that would say that this counting range gives the best classification of children's understanding of the successor function. We changed a few things. You can test them at least 6 numbers produced, tested at least 5 out of 6 right as a criterion, or 4, at least 3 out of 4 right. All the results are the same in the next table. So here is a study, right? So we divided kids into ranges of counting by the decade. Okay, so several metrics here. You can do F-score, just really standard classification stuff. You can do accuracy. You can do Matthews correlation coefficient, which is useful for comparing sets of different sizes. You can also use a decision stump technique for machine learning. So for these metrics, the larger the better, but this metric, the smaller the better. So you can see 50 is really the best classification of kids into successor function knowers and non-knowers. We also, and it's better than the counting range before or after. And if you do this by age, the best performing age is 4.8. And it's nowhere near as good as the counting range. So age doesn't really tell you much about successor function development. It's correlated, of course, right? But it's much more direct predictor is really how high they can count, not the age. So that means that probably general cognitive development isn't what's driving the understanding of the successor function, but counting is. But this is probably even better analysis of the data. Okay, so we classified children into non-productive counters, namely kids couldn't count past 50, and kids who could count past 50. There are 2 subgroups here just to make things interesting, right? We have one group called the 48 to 49ers, namely a Cantonese learning child who could count past 40 but not past 49. So just below the threshold. And then there's another group we call 50 to 59ers that could just count past 50 but couldn't pass 59. Okay? So this you would expect a dramatic difference between the 2 sets of kids, and indeed there's a case. The blue bars are the performance on medium numbers. The red bars on large numbers. Of course, these kids couldn't count past 50, so they're not tested on the large numbers. And this is the chance. Chance is 50%. So you can see for unproductive counters, it's not significantly different from chance. If you do a binomial test. And what's interesting here is about the kids who are just below and kids who are just above. If you look at the kids who are just below 50, they're at chance. If you look at kids who are above 50, they're way above chance. If you also compare the children's behavior on the medium numbers and the large numbers, you can see there's actually no difference between the performance on small numbers and large numbers, indicating that once they get it all the way. And I can give you more anyway, so you can see there's no difference between this group and that group, and there's no difference between the 15 to 59ers and the rest of the high counters. I can give you more, but I won't. Okay, so everything is showing that is really counting past 50 as a categorical predictor that best predicts how well they do. Their age And once you cross the threshold, how high you can count really doesn't matter when it comes to their performance. There's some immediate consequences we can skip. Okay, let's talk about the more interesting questions. Is it too Whorfian for comfort? Absolutely. So here we say that, again, the CP knowledge is the same between English and Cantonese kids. But Cantonese kids learn the successor function a whole year ahead of American English learning kid. As far as we know, this is really due to the simplicity of the language. It enables them to learn the regularity much more effectively. This also corresponds to a lot of other studies showing that in languages where you don't have a productive counting system, you don't have the conception of symbolic numbers, at least in the conventional test, they eventually can acquire it, but that requires learning of a second language that does have a productive counting system, as is well known. So you can think about this as that I would argue that symbolic numbers are really a set of concepts enabled by language-specific morpho-phonological acquisition. So my favorite example here is this anti-missile thing in linguistics, right? So anti-missile, you can embed this as long as you want. You have no idea what an anti-missile is. You have 75 antis. You have no idea what that means. But you know adding 1 is going to negate that, right? So the same as saying you have no idea. You may have very clear, concrete understanding of what 3 or 4 is. A small number, you can visualize them, you can supertize. You have no idea what 87 is. It's just abstract concept. You know whatever the concept is, add 1 is going to give you 88. That's all there is to it. It enables you to generalize the successor relation from very small numbers where you know either innately or learn by rote all the way to infinity. So I was very surprised by this sort of neo-Whorfian perspective echoed in Jerry Fodor in his very last book. So here's a quote I was discussing with Alex Gleiman. So here's a quote where he's basically talking about us and other animals, right? So except us, nobody can respond or refer to or remember or even think about anything that isn't or hasn't been within its own world, right? So this is talking about other animals. They cannot go beyond their perceptual experience. We're exempted. We can refer to Genghis Khan because there's an intricate system of linguistic contrivances, not language thought, very importantly, not language thought. He was really talking about a particular grammars of real languages, of English, French, Urdu, and so on. So this really seems to be suggesting that these concepts are enabled by learning the linguistic rules in which these concepts are encoded in your native language. And then this numbers would be an example. You generalize from finite experience directly from perception then all the way to much more general and systematic knowledge of cognition. So to wrap things up, so here's an example of how linguistic form can facilitate conceptual development. We provide a mechanical theory of how form can drive meaning, certainly extendable to other conceptual domains. And this is the next step. And also, I think somewhat surprised by saying this, that this really pushes us from a super nativist perspective, which is the one I had early on in my career, to a neo-Whorfian, neo-constructivist perspective, that we really build things up where the glue is really language, but we need to say more than just waving our hands saying language makes us smart. You really have to provide a concrete competition model of how this generalization process takes place. And maybe that can explain a whole lot of other things in addition to number cognition. So I would thank some of my collaborators and people who paid for it, and thank you for listening. Sorry, I took longer than allocated.
Okay, then we'll wrap this up. We're out of time anyway. If you have questions, please send them to